I'm going to talk about CHERIoT Audit, which is a thing that we built actually a while ago and that we designed CHERIoT to support from the scratch, but is not one of the things that we talk about the most. I think that the key thing I want to get across is memory safety is great, right? And fixing 70% of security vulnerabilities is obviously a good thing. But that wasn't the starting point for Cherry. The starting point for Cherry was we want to do fine-grained compartmentalization. And it turns out to do fine-grained compartmentalization, you need a programmer model. And a programmer model needs to be able to share things that programmers care about, which are objects, not pages. And that means you have to be able to enforce memory safety at object granularity. And if you can do that across compartments, you can do that within a compartment, and that's great. And now we're at this place of 70% of security vulnerabilities addressed by Cherry, hooray. But it was never the end goal. It was a building block for the most interesting things that we can build, and that's what I want to talk about a little bit today. So many of you have seen a variant of this slide. CHERIoT, we build our security guarantees in layers. And we start with these two core guarantees that Cherry gives you: no buffer overflows, no pointer injection. Any Cherry platform will give you that. And we have no use after free, and we have some lightweight control flow integrity enforcement. And those are the foundational guarantees. We've talked about those a lot. They're not surprising to anyone. And neither really is the fact that we can do compartmentalization, that you can limit blast radius of vulnerabilities or just logic bugs. And that you can protect secrets in safe boxes. But then around that, we want to be able to reason about what these compartments can do, and we want to be able to write policies that say, I've got this bit of third-party code that I got from a supplier I don't trust, or from a random GitHub repo that is definitely not written by North Koreans, or that I vibe coded and is definitely not full of maliciously introduced training data. And I want to be able to say, if that is actively malicious, what is the worst that can happen? And we built our ABI and everything on up to allow you to do that kind of reasoning. So in a CHERIoT system, at the most reductionist, a compartment is two things. It's some code and it's some globals. And you find these from two registers. The program counter capability points to your code. Your global pointer points to all of your read-write globals. And if you look inside that code region, it's actually not quite code, because it turns out it's really useful to do PC relative addressing to find read-only globals. So we stuff those in there. And we also have an import table. And if you zoom out a little bit, there's also one other thing that a compartment has, which is used only by the machinery for doing compartment transitions and by the loader. And that's an export table. And so these two regions in memory for any compartment describe between them either everything exported from that compartment and everything imported into that compartment. So when the system sets up that initial PCC region and that initial global pointer region, those can have capabilities in them, but only capabilities that point to those two regions, except for that import table. And this means that we have two places for the linker to look, and two places for the loader to look for instructions for initialization for everything that describes the graph of all connections between compartments and between compartment and other things. And there are a bunch of other things. So we have static sealed objects, which we use for building a software capability system. I'll give you a couple of examples of that later. We have objects that are shared statically between compartments. We have functions imported from other compartments and shared libraries, and in a CHERIoT system, a shared library is stateless. It doesn't have that global pointer, it just has the code pointer. And so when you invoke it, it's treated as if you're not doing any kind of security domain transition. You call it just via a sentry, you go there directly, and functions like memcopy, all of the soft float things, and a load of stateless functions can then be shared between many compartments. And this scales up to slightly larger things like a JavaScript VM. They can all be shared between compartments because they don't own state. They just allow you to provide state as arguments. And if you want to then wrap those in a compartment to ensure that they can be used in places where actually you shouldn't have access to that state as a caller, that's also fine. And we have sealing keys, which are exported from functions and from compartments and imported and are used to link those sealed objects to something that is meaningful to a programmer in the type system. And that's really important because it goes back to this idea that we came to very early on in the Cherry project, that these abstractions are not just about security, they're about being able to understand what your security guarantees are by reading the source code, not by looking at some other policy off in some other description as you get with something like SE Linux. So starting from that layout in memory, the linker is going to generate, when it links a firmware image, an enormous amount of JSON, and this is actually usually larger than the ELF file it generates. JSON is not, it turns out, the most dense encoding of data. And so it'll have, for each compartment, some things saying, this is the kind of thing you're exporting, and in this case it's a sealing key, and this is the key that is used as a sealing O-type to identify the software capabilities that authorize you to allocate memory. And I'll show you what the port for one of those looks like in a little while. But you also have this for functions, and functions will tell you, does this run with interrupts enabled or disabled, which maybe if you're writing application code doesn't matter, but if you're writing real-time code, it's really nice to be able to say which functions will ever run with interrupts disabled. It tells you the number of arguments that are passed in registers. Mostly this is useful as metadata for the switcher, but you also might want to have a policy that cross-references that with the types that are exposed and says, hang on, I'm only passing you one argument, but you're claiming that 4 arguments are passed in registers, so I'm just going to leak whatever happened to be in those registers. And it does the same thing for import. So for each entry in that import table, you'll have something maybe like this. So this is a shared object that describes the revocation epoch, the epoch for coordinating our lightweight claims mechanism. And you can tell from this particular one, this is the import in the allocator compartment, because this is the only one that has permit store permission, whereas every other compartment will have a read-only view of this, so it can be used for some lightweight synchronization to say, I'm trying to update a thing in a mostly lock-free data structure. Has it been modified out from under me? Do I need to do it again in a little loop? And you can then later on write a policy that says, actually the allocator really should be the only thing with a read-write view of this object. But you also have this for memory-mapped I/O devices. So you can say, I think this one is the part of the temporal safety mechanism, again assigned to the allocator. Each device will have its fixed location in memory, its size, and you can see which compartments have access to it and what rights do they have to access that. So for some devices where reading is side effect free, you might allow multiple devices to have read-only views of that device. For others where reading is popped from a FIFO, then you need to restrict that more. I said we have this lightweight software capability mechanism. This is actually one of the capabilities that authorizes you to ask the memory allocator to allocate memory for you. And you can see in the sealing type field that this must be sealed with that key from that first export. And you also see the contents, and so you can decode that and you can say, oh yes, this is allowing me to allocate up to this amount of memory. And this is not something I ever want anyone to actually look at. Right? This is a huge pile of JSON, and no one wants to read a huge pile of JSON. But fortunately, this is a problem that appears elsewhere, and particularly in a lot of cloud systems. And so the Open Policy Agent project has a language called Rego, and this is how they think Rego was designed. I think they took Prolog and Python and JavaScript and they put them in a blender and they forgot to put the lid on and a load of bits came out. And Rego was what was sort of left in the bottom tangled around the blades. But it's a language that is designed for writing policy over JSON documents, which is supported by a bunch of other projects, so it's not a thing we're just making up. And this is the language that the CHERIoT Audit tool uses for writing this kind of query. So you can use Arago list comprehension to say, for every compartment, for all of its imports, please filter them based on, are they allocator capabilities? So are they sealed with that particular sealing type? And if they are, construct a list for me of just the quota field from those, and then use the sum function to add all of those together. And now you know what is the maximum amount that all of your compartments might try and allocate if they all allocated together. And you might want to say, well, that probably should be less than all of memory, or maybe it is allowed to be 20% more than all of memory because some overcommit is nice, or maybe all of them must add up to this amount, but this one is allowed to allocate a bit more, or policies like that. We can do much richer things. So this is a query that the network stack's reusable block of Rago provides. This lets you say which of my compartments is allowed to ask the TCP/IP stack to connect to a remote host, and what remote hosts are they allowed to connect to on which ports, which protocols. And again, remember, these are capabilities. So these are not just this compartment can do this, but this compartment might ask the TLS stack to connect to this server on its behalf. Capabilities can be delegated. That's one of the things that makes them so nice. And you might want to say, well, can unencrypted data leave my device via a TCP socket? So maybe you ask, well, who is allowed to call the function in the TCP/IP compartment that sends data? And hopefully you get a list that has one element in it and is the TLS stack. And once you've done all of that introspection, you start wanting to write policies that you can use to drive code signing or CI or other kinds of automatic checks. And again, this is what the audit tooling was supposed to do. So if you want to say, well, that function, that list that I had of just the TLS stack, that is the correct answer, and that must always be the correct answer, you can say the allow list for calling this function from the TCP/IP stack is the TLS compartment. And if anything else calls it, policy fails. And just like Prolog, the answers are yes or fail. Similarly, your core local interrupt controller probably shouldn't be accessible by anyone except the scheduler. So again, that's a thing that you can write in your policy. You can do the same thing with pre-shared objects. So our SNTP compartment exposes a little shared object that tells you what the cycle time was last time it did an NTP sync and what the actual wall clock time was, so you can then compute what the current wall clock time is from those two values. And it should be the only thing that has write access to that, but anyone else can read that object, and so you can have a policy that says the allow list for things having write access to that object is, again, just that one compartment. So to quickly sum up, what we're trying to enable here is fearless code reuse, the ability to take code from wherever you want, use it, and understand the worst that can happen if it's actively malicious. And we started by designing an ABI that made it easy to capture all of that information. We have a linker that then serializes that in an incredibly verbose and not at all human-friendly form. And I had at least 5 slides explaining to you why you never, ever want to look at that. And then we have tooling that allows you to write something in an approximately human-readable language to express policies over that. And I have 38 seconds left, so I'm going to give you back some time. Thank you.